Hello aspirants, welcome back to SKD's Note. So in previous class we have discussed about transformers, statically induced EMF, types of statically induced EMF and mutually induced EMF. Okay, so along with that we have studied magnetic coupling, how the magnetic coupling is taking place, like notations and all, and also we have discussed about construction of transformer, what are all the parts we have in transformers, like we have transformer core and transformer winding. So we have discussed about transformer core also, how the transformer core is made up of. Okay, and we have studied about what is CRGO steel, why it is used. Okay, and laminations, stacking factor, etc. So today we are going to discuss about how the windings procedure, that is we are talking about windings today, transformer windings. So here you can see that here primary winding and secondary winding, correct? So basically transformer windings are made up of what? Transformer windings are made up of either copper or aluminum. Windings, copper or aluminum. Okay, remember this. So here copper windings are used in power transformers. Okay, power transformers, whereas aluminum windings are used in distribution transformer, where you can see in your nearby home. Okay, that is 11 kV bar 440 volts distribution transformer. Okay, remember this. So windings are not made up of single solid conductor because of additional stray load losses. Okay, so windings are made up of stranded conductors. Like how we say multi-strand conductors, like you will be having so many stranded conductor. Okay, instead of solid conductor, like we used to have in olden days, like back in 90s and 80s. Okay, why we will use stranded conductors? To reduce stray load losses. In order to reduce stray load losses, we will use stranded conductors. Remember this. Okay, so stranded conductor also useful to reduce skin effect. Okay, these conductors, it is what ACSR you studied, right? Like that. So reduce skin effect, since skin effect is proportional to square of the diameter of the conductor, correct? So if we talk about winding procedure now, so here we can see that two winding core transformer, this one, and here you can see core transformer with interleaved windings. Okay, so in core type each winding is divided into two equal parts, are placed on two separate limbs. Okay, equal parts and placed on two different limbs. This is limb 1 and this is limb 2. This process of distributing same windings on two separate limbs is called as interleaving of windings. Okay, the main purpose of using interleaving windings, here you can see, okay, these are equal, but here what we are doing, we are making two equal parts of LV and HV, so placing in different limbs. Okay, so the main purpose of using interleaved winding is to reduce the magnetic leakage flux. What here it will go na, since we are using core type, here we are talking about core type, we know that there will be more magnetic leakage flux in core type transformers compared with shell type transformer. Okay, so as half of HV, here you can see here half HV, here half HV, and LV are placed on same limb, HV half HV and half LV placed on same limb. This winding procedure is also called as concentric, okay, concentric winding. Okay, I will show you in next picture. So this winding procedure employed in core type of transformer is called interleaved and concentric winding. So here you can see concentric winding, this is how it is made up of. Here you can see this is HV winding, here this dot means it's going, it's coming out, where this cross means it's going in. So this is thick layer is called HV insulation. Okay, then we have LV conductor windings. Okay, then we have LV insulation, same wise this way also. Understood? So leakage flux here it will be reduced in concentric windings with insulation, which I have shown you here. Okay, so here we know that we are keeping LV winding, okay, LV winding near to the what, core. Here you can see LV winding is very near to the core instead of HV winding. What are all the advantages if we keep the LV winding near to the core? Okay, in concentric winding procedure, LV is placed near to the core to get the following advantages. Okay, we will see those now. So it reduces the amount of insulating material, reduce amount of insulating material. So then we have next, it also reduces the amount of copper required. So it will also reduce amount of copper required. Understood? So then also due to above reason, size and weight of the and cost of the transformer reduces. Yes or no? Copper required, see we will give more amount to the insulating material, that will be reduced in the cost perspective and size also. Okay, overall cost reduces by considering above terms. Okay, it reduces the leakage flux in the transformer, it reduces the leakage flux in the transformer. Then what else we have? It provides an easy access to HV winding to provide tappings of voltage control purpose. Okay, these are all the advantages of keeping LV near to what, core. These are all the advantages we have. So now if you talk about the direction of current in windings, so here you can see in this diagram, if the windings are placed on separate limbs, okay, without interleaving, that means half of the HV is placed in same limb where LV also placed in same limb. Okay, that is not the case in this case. Okay, so here without interleaving, they must carry currents in same direction to satisfy the transformer action. Okay, here you can see it's going inside, coming outside. Here also it's going inside and coming outside. So same direction of current and same direction of flux. Here you can see here this is flux due to high voltage HV winding and flux due to LV. So if the windings are placed on same limb, now this is case 2. What happens if the same limbs are same windings are placed in the same limb with the interleaving, they must carry current in opposite direction. Here you can see LV is going upwards and current of HV is going downwards. Okay, this direction is to satisfy the transformer action as shown in this figure. Okay, windings are placed on same limb means the direction of the current will be different, whereas windings are placed in different limbs, the direction of current will be same. Okay, so according to Lorentz principle, if the two parallel conductors are carrying the current in same direction, okay, same direction, what happens? So there will be a force of attraction between them. If the two parallel conductors carrying current in opposite direction, that is like this, what happens? There will be force repulsion. Here force attraction. This Lorentz law you will see in measurements also, very important concept. As the windings are placed on the same limb carries the current in the opposite direction, as we saw here. See, it's going upwards for LV, it's going downwards for HV. The nature of force between the winding is repulsive according to Lorentz principle. These repulsive forces also called as a radial forces because of forces are perpendicular core. So the repulsive forces are exactly equal and opposite to the normal operation of the transformer. Okay, so the resultant force will be 0. So now if you talk about the shell type of transformer, this is arrangement of winding in shell type transformer. So here you can see that all are sandwiched. Like if you take bread, you will be adding some something called you can keep any vegetables in between, it will be called sandwich. Likewise here in a winding between there will be a layer of insulation between two windings, that is LV and HV. It is called as what? Sandwiched. So in shell type of core, each winding is divided into certain sections and are alternatively placed. Here you can see LV, HV, LV, HV, LV, HV. Okay, so on here on middle limb, so this process is called as sandwiching. Okay, here you can see, here I am showing only one, so this will be central limb, so here it will be like this. So the main purpose of using sandwiched winding procedure is in shell type transformer core is to reduce the magnetic leakage flux. In core type of core, we have seen that there will be huge magnetic leakage flux. So in order to reduce the magnetic leakage flux, we are going with interleaved concentric windings in core transformer. In shell type transformer, we are going for sandwiching technology. Okay, so here it will be symmetrical distribution of windings is taking place. See here HV1, LV1 and HV2, LV2. HV3 and LV3 are divided here. Okay, understood. So the arrangement of sandwiched windings procedure with 3 sections of LV, correct, LV1, LV2 and LV3, and 3 sections of HV1, HV2, HV3 high voltage windings. So the leakage flux on the magnetic potential difference across each section of the winding, okay, if the leakage flux of a total HV winding is phi, then the leakage flux with 3 HV sections, what it will be? If it is phi, then leakage flux due to all 3, it will be phi by 3 HV windings. Understood? And the same is applied for LV also, correct? So in shell type of transformer core, extreme LV winding section should be contain 50% of turns. Okay, extreme means these. Okay, so when compared to inner LV windings section, to get symmetrical distribution of the windings, as I discussed here. Okay, so what it will do, it will give the good mechanical stability for the windings. Under normal operating conditions with symmetrical winding distribution, what happens is nothing but only axial forces are present in shell type of core. Under abnormal operating condition, what happens? In addition to axial force, there is a possibility of getting radial force also. That means like opposite forces, not in same direction. So the radial force makes the windings to shift towards radial direction. Understood? So now we will discuss about some window factor here. So what is window factor? The window factor of the core is an important design parameter which determines the amount of leakage flux in the transformer. What it defines? Amount of leakage flux. Understood? So winding factor is calculated as height of window divided by width of the window. Here you can see the same thing we are placing here on the middle limb or central limb of the shell type transformer. From here to here it is called as height of the window, and the remaining part here, from here to here, it is called width of the window. Okay, here more the window factor, lesser will be the leakage flux. Okay, more the window factor, lesser is leakage flux. Understand this first. Okay, suppose in shell type core, window factor is more since height is more and width is less. Okay, you can note it down. In shell type, window factor is more since height is more, width is less. Whereas in core type transformer, window factor is less. Window factor is less in core type core. Why? Since there is more width, less height. Okay. I think you have understood till now. So now if we talk about the ideal transformer, what is this ideal transformer? Transformer at stand still. So first we should know what are all the assumptions should be made when it is ideal transformer. First thing is the permeability of the transformer core is assumed to be infinity. Okay, this is what permeability. Assumed infinite. Okay, you write in infinite. Okay, don't use this thing again, you will be get confused. This is one assumption. Another assumption, iron losses in transformer core are assumed to be 0. Iron losses are assumed to be 0. Okay. Then we have resistance of transformer windings are also assumed 0. Resistance of transformer winding is are assumed to be 0. Then again we have magnetic leakage flux in the transformer completely 0. Magnetic flux leakage completely 0. And the last one we have the magnetization curve of transformer core is assumed to be linear. Magnetization curve of transformer core is linear. These are all some assumptions made for ideal transformer. Okay. So transformer with finite permeability core, if we talk transformer with finite permeability of core. So here what happen? So when the transformer is excited, that is transformer is excited with rated voltage and frequency, it draws excitation current called magnetizing component of current. It draws a exciting or excitation current called magnetization of magnetizing component of current for creating flux in the core. Okay, understood? So that magnetizing component of current is represented as I mu, that is Im sin omega t. Okay, what is this? Magnetizing component of current for creating flux in the core. So primary MMF, that is magnetomotive force, will be, we know that basic MMF will be Ni, okay, where N is number of turns and I is current. Okay, so here we are considering it as N1 and mu 1, sorry, I mu, N1 and I mu. Therefore here I mu is, we are writing it as Im sin omega t. Okay, so let me draw here first. Then you will understand. Okay, so here this is winding. When rated voltage V is applied with rated frequency, there will be a magnetic component of current, which will in turn produces an flux in the core, that is phi m, main flux. Okay. So in primary winding there will be a current. When there is a magnetic coupling taking place, secondary windings also get energized. Due to that, there will be a what? Current in secondary winding also takes place when load is connected. So here we know that flux is nothing but mmf by reluctance, correct? So here just now we have written N1 Im sin omega t, reluctance, resistance in electrical, reluctance in magnetic circuits. Okay, or let me represent like this. So phi will be phi m sin omega t, where phi m is nothing but N1 I m divided by R. Maximum mmf divided by reluctance. Okay. So from Faraday's second law we know that from Faraday's second law, from Faraday's second law we know that induced EMF, this is self-induced EMF here, so it will be minus N1 d phi, we know that. Okay, what it is? Phi m sin omega t, then it will be E1 equals to N1 phi m, differentiation of sin what? Cos omega t, and differentiation of this thing, what t is? Omega. Omega t is omega. So then it will be N1 phi m cos omega t into omega can be written as cos omega t minus 90 degree. So self-induced EMF in primary winding is lagging behind the flux by 90 degree, correct? So this minus represent what? Lenz's law. At omega t equals to pi, what we have? EMF is maximum. Remember this. Okay. So E1 max will be N1 phi m omega, that is maximum. RMS value of induced voltage will be RMS value of induced EMF will be E1 equals to E max divided by root 2. Here N1 phi m, omega is nothing but 2 pi f, correct? Angular velocity, divided by root 2 into 4.44 N1 5 m f, this is frequency. So here E1 equals to 4.44 N1 5 m f. Here we can say that phi m will be B max divided by A n. This is from flux density. Okay. B equals to phi by A. This is what magnetic flux density. With the help of this we got this. Okay, let me write it properly. B max into A n. So here E1 will be 4.44 into N1 Bm An F. So here An, where An will be what? Net cross sectional area of the core. Net cross sectional area of the core. Since core is laminated, we have Ag will be L into B. So therefore An will be Ag into Ks. Here Ks means what? Stacking factor. Similarly, same for secondary side, that is E2 will be minus N2 d phi by dt. Okay, and you will get the same thing. E2 equals to 4.44 N2 Bm An F. Okay, these are all the EMF equation. Okay, so these are all EMF equations of transformer. Okay, so if we talk about vector diagram, here V1 will be minus E1 according to what? Lenz's law. Correct. So this is what? Flux phi. There will be voltage lag by 90 degree, that is V1 equals to minus E1. Okay, here 90 degree, so E1 and E2 are in same direction. Okay, here you can see. So in order to satisfy Lenz's law, you are applied voltage here and EMF induced is opposite to each other in Lenz, according to Lenz's law. Okay, here it is I mu, magnetizing current. So from observation of equations of EMF 1 and 2, that is E1 equals to 4.44 N1 Bm F An and EMF E2 4.44 N2 Bm F An. EMF per turn on both side of transformer is same, correct? So EMF per turn will be 4.44 Bm An F. Okay, so from this we can say that E1 divided by N1 equals to E2 divided by N2. It can be written as E2 divided by E1 equals to N2 divided by N1 is called as transformation ratio. Okay, this is called as transformation ratio. Understood? Voltage rating mentioned on the nameplate of the transformer represents the induced EMF only. Okay, there will be a nameplate of voltage rating on the transformer. So during operation of the transformer, okay, now if we talk about during operation of transformer, the maximum flux density in the core is proportional to V by F. Maximum flux density, that is B max, is proportional to V by F. If V by F constant, ratio of voltage and current is constant, then maximum flux density is constant. Remember this key point. Okay, by keeping applied voltage constant, if the frequency of the by keeping applied voltage constant, if we increase the frequency or reduce, if the frequency of the transformer is reduced, then the Bmax in the transformer core increases, which drives the transformer core into deep saturation, thereby demands a very high excitation of current or voltage from the source. Okay, you need to apply more and more voltage. Okay, suppose that's what, if frequency gets reduced, automatically this flux density, magnetic flux density will increase, correct? So with that, I mu, that is magnetizing current, also increases. This phenomena is called overfluxing of transformer. Therefore never reduce the only frequency by keeping applied voltage constant during the operation of transformer. In order to operate the transformer at good condition, you need to keep the V by F ratio constant. Okay, you should not only reduce the frequency. If necessary to operate the transformer at reduced frequency, then the applied voltage should be also reduced along with the frequency. If voltage reduces, frequency also should reduce. Okay, you should remember this, such that V by F ratio should be kept constant. So if we talk about next, so for given kVA rating, so now we will talk about this. For given kVA rating of transformer, more the design frequency, lesser the cross sectional area. More design frequency, less is the cross section area. Okay, and lesser will be size and weight of the transformer. Therefore less weight of transformer and size. Okay, higher the design of the transformer, lesser will be the specific weight of the transformer. Okay, specific weight of the transformer will be equal to the weight of the transformer per kVA rating. Okay, you should remember that. For a given kVA rating and design frequency of transformer superior, the magnetic material used for the transformer core, okay, the magnetic material which we are using for the transformer core, higher will be the flux density and lesser will be the size of and weight. Suppose Bmax, okay, of the core, magnetic material, if we are using, the maximum flux density is higher, then there will be less less weight of transformer. and size also. Superior the magnetic material used for transformer core, lesser will be specific weight of the transformer. So you should have good magnetic material used for the transformer core. These are the some observations and important key points to remember while studying the transformer. Okay, so in next class we are going to discuss some of the problems, okay, on these topics. Till now we covered. Later we will move on towards what, how this difference between active and reactive component of current, okay, and other concepts like equivalent circuit of transformer, no load at no load and transformer on load, okay, and some vector diagrams and etc. Thanks for watching this video. If you like this video, please like and share with your friends. Thank you.